Today we're doing a bit of a forensic analysis, really, on a piece of metal that should have been just about invincible.
Yeah, we're looking at a 2026 study by Alexander Sulemanidze.
And the subject is this nickel-based superalloy, EI698VD. This is the kind of material you build gas turbine engines out of.
Exactly. I mean, these parts, the turbine discs, they have to withstand up to 750 degrees Celsius while spinning at incredible speeds. They have to be stable.
But this study found that under certain conditions, a specific batch of this alloy didn't just bend or break.
No, it fundamentally changed its behavior.
And that's our mission for this deep dive, to figure out what microscopic poison turns a tough, ductile metal into something that just snaps.
It really does read like a crime scene investigation. So to find the culprit, the researchers ran a pretty standard test.
The monotonic tensile test.
Right. They took little cylinder-shaped samples of the alloy, put them in a furnace, and heated them up.
All the way from room temperature up to 700 degrees C.
And then they just pulled them until they broke.
Okay, so looking at the data, things seem pretty normal for a while, but then you hit 550 degrees Celsius.
That's the tipping point, the critical threshold. Below that, the metal stretches. It's ductile. But once you cross 550...
The plasticity just falls off a cliff. It gets brittle.
Exactly. But the really interesting part isn't just the break itself. It's what happens during the stretching, between about 400 and 700 degrees.
You're talking about the Porteven-Le Chatelier effect.
The PLC effect, yeah. You can see it on the charts as serrated flow.
It stops being a smooth curve and starts looking like a saw blade. It's all jagged.
And that jagged line is basically a picture of a microscopic battle. To stretch, metal needs little defects called dislocations to move around.
Yeah.
But in this specific temperature range, other impurity atoms start moving fast enough to catch those dislocations and pin them down.
So the metal tries to stretch, but it gets stuck.
Right. Stress builds up, snaps it free, then it immediately gets pinned again.
And that catch and release, that stuttering, is what makes the line on the graph so jagged.
Precisely. It was a huge clue, but it was still just a symptom. To see the real cause of death, they had to look at the fracture itself.
So they couldn't have broken pieces under a scanning electron microscope.
And this is where the picture becomes crystal clear. At lower temperatures, the breaks were transgranular.
Meaning the crack just tore straight through the individual metal grains, a typical high-energy fracture.
But above that 550-degree threshold,
it switched.
It completely switched to an intergranular fracture. The cracks stopped going through the grains and started going around them.
The metal was literally unzipping along its seams, like the mortar in a brick wall just dissolving.
A perfect analogy. So the next step was obvious. They had to analyze the chemical makeup of that mortar.
Using energy-dispersive X-ray spectroscopy.
Right.
And they found it. The impurity.
Lead. Just plain old PEEB.
Which is a complete disaster in an aerospace alloy. The allowable limit for lead in this material is what? Less than 0.0001 per.
It's incredibly strict. But this batch...
This batch had 0.09%.
Yeah. 90 times the acceptable limit. A catastrophic quality control failure.
And that explains everything. Because lead doesn't dissolve in nickel, and it has a really low melting point.
So when that engine part gets hot past 550 degrees, that solid lead, it isn't solid anymore.
It melts, and it migrates to the grain boundaries.
Exactly. It forms this microscopic liquid film between the solid grains. It's called liquid metal embrittlement.
So it's not even holding the alloy together anymore. It's actively lubricating the path for the cracks to form.
It's terrifying. You're talking about an impurity that's less than 0.1% of the total mass.
And it compromises the entire structural integrity of a critical engine component.
It just shows you that in advanced manufacturing, controlling the chemical composition isn't just some final check, it is the safety system.
A truly invisible flaw acting like a ticking time bomb.
Absolutely. And it really leaves you with a final unsettling thought. If an impurity this tiny can cripple a superalloy, how many other critical infrastructures, bridges, reactors, engines, are operating right now with a bad batch of their own, just waiting for the temperature to be right?
Something to think about. Thanks for diving in with us.